everyone, thank you for the welcome. My name is Oliver. I'm from the Google Open Source Security team. Really sad to not be able to make it to VonCon in person this year, but I'm grateful to still have the opportunity to give this talk. Let's jump right in. Yeah, so the open source vulnerability schema, which I'm going to be talking about, or OSV schema for short, is a JSON schema we created as part of the OpenSSF for describing known vulnerabilities in open source packages. It's a very minimal schema, and as you can see here, we can actually squeeze in the entire schema structure into a single slide. So the schema was started about 4 years ago and has since seen adoption from most major language ecosystems and open source vulnerability databases, as well as Linux distributions. And one of our goals here was to foster a community-maintained, easy-to-use and comprehensive database for vulnerabilities. And we wanted to do it in an open source friendly and developer friendly way. So today we have almost 300,000 advisories collected across 31 ecosystems and 21 vulnerability databases. So I wanted to talk about some of our guiding principles for the schema that we use for designing changes and additions. I've roughly categorized this into 6 principles. So the core use cases, simplicity, correctness and consistency, prioritizing open source, federated database model, and backwards compatibility. And I'll go through what all of these mean. So when we first started this schema, we didn't actually have a lot of these very well thought out. So some of these, actually many of these, are the result of years of iteration and a little bit of looking back and reflecting on where we think we made the right choices. Let's start with the first and most important guiding principle for us, which we prioritized from the very beginning. This was to build a format that was laser focused on solving a primary goal, which is to enable software developers to accurately identify and remediate all known vulnerabilities in their open source dependencies. The emphasis here is on this being actionable, with the recognition that software developers are often the ones at the receiving end of all vulnerability reports and are the ones being asked to resolve these issues. So this goal breaks down into 2 categories of users that we need to cater towards. The first is vulnerability databases, where we obtain all of our vulnerability data. So the format needs to make it easy for any vulnerability database to adopt and export, and also be able to enable databases to express all of the information that they want to express. The second is vulnerability scanners, which connect software applications and SBOMs to vulnerability databases. Scanners need to be able to produce automated, actionable, and accurate results using the feeds formatted in the OSV schema. Now, these aren't the only types of users that need to consume vulnerability data. For example, researchers might be interested in performing analysis of vulnerabilities that require richer information than what a vulnerability scanner needs. We generally consider these out of scope in that while we want to support these use cases, we wouldn't want to make any changes to support them that will compromise some of our main goals. And I'll talk a bit more about this later. This leads us to our second guiding principle, which is simplicity. So a well-defined set of use cases allows the schema to remain concise and minimal. So the simplicity makes the schema easier for consumers to understand and easier for producers to adopt. Each field should serve a distinct purpose directly linked to the core use cases. And there must be a practical way for vulnerability data producers to supply the data for each field. So aspirational fields, which can't be realistically populated by databases, nor realistically used by consumers, must also be avoided. So I wanted to go into some examples of important fields and how they relate to the use cases that we outlined. So when we first started out the schema, we quickly realized the need for a field to mark a vulnerability as an alias of another. This is because it's common for there to be many different IDs used to refer to the same vulnerability. For example, the GitHub advisory database uses the GHSA- prefix, and the Go vulnerability database uses the Go- prefix. The clear use case here for vulnerability scanners is that they need a clear way to deduplicate between different IDs for the same vulnerability when it comes to addressing them. Now, aliases aren't the only kind of field for recording relationships between vulnerability records. There could be many others, but we only want to record these relationships if they tie back to our use cases. So one recent relationship field we added was the upstream field, to record vulnerabilities where one is upstream of another. A common example here is Linux distributions, which often issue their own advisories based on upstream CVEs. For example, the Ubuntu distribution issues Ubuntu security notices prefixed by USN, which often also bundle multiple CVEs into a single record. Aliases wouldn't work here because of this bundling. Aliases would mean that every single bundle CVE is the exact same, which is incorrect. So the justification for adding upstream was that there was a very clear use case. When a user is scanning a Linux machine or container, users want to know if it's affected by a specific upstream vulnerability, such as a CVE. And if we record this upstream relationship, then there's a very clear and automatable way to reason about this. And one of the most important pieces of a schema for vulnerabilities is enforcing consistency and correctness. So historically, many, including Google, have had a lot of challenges with leveraging vulnerability feeds like the MVD or the CVE list in a machine automatable and consistent way. It was often really difficult to map those vulnerability feeds to the actual package names and versions used in actual software in a predictable way. This really shouldn't be the case, particularly for open source ecosystems, which have really well-defined namespaces and versioning rules. So as such, the OSV schema, we try to strive to follow upstream rules for relevant ecosystems, and we also try to enforce specific ways to encode and capitalize different fields so that the producers know exactly what to output, and consumers can confidently know how to consume the data in a consistent way. The two examples here are the Debian and PyPI or Python ecosystems. So Debian has many different ways to refer to their specific releases via either their code names or version numbers. And even these version numbers have some ambiguity. They could either be floating points or they could be integers. So here in our OSV schema, we enforce a specific way of encoding Debian releases to enforce consistency by referencing some authoritative list that Debian provides. PyPI also has really special rules for how to normalize and treat package names. There's actually an infinite number of ways to refer to the same Python package in the PyPI package ecosystem. So in our schema, we recommend, or we actually enforce, that PyPI package names are normalized according to the rules that are set out in Python. Another example is the Maven ecosystem, which has really complicated rules for how version ordering is done. So version ordering is very important because it's necessary to match software components to vulnerability feeds. And we found that most open source ecosystems define their own set of version ordering rules that differ quite a lot. This means we need to treat versions in different open source ecosystems very differently, as there's no generalized way to compare version numbers in a vulnerability feed. They really depend on the package ecosystem that package came from. Even Semver itself is a bit of an overloaded term. So the official Semver 2.0 spec points to some very clear and unambiguous rules for version precedence and ordering. But in practice, very few ecosystems actually follow these rules. So in a schema, we distinguish between the strict Semver ordering as defined by the Semver 2.0 spec and ecosystem, which refers to the specific rules for the relevant ecosystem. We also set out very clear rules for evaluating if a package at a given version is vulnerable according to a record by providing pseudocode that shows how to implement version matching using OSV data. And as we're dealing with open source, we don't just stop with linear version ranges. open source also has the benefit of a source code and version control system information being available. So the same versioning scheme and evaluation rules we define generalizes pretty well to also handle nonlinear Git versioning trees with different branches. So in this example, we have a Git commit tree where all the branches are vulnerable except for one containing a fix. And we encode this in pretty much exactly the same way as how we encode vulnerabilities for linear version ranges through the introduced and fixed events. The semantics here are that unless there is a fix specified within a branch, that branch is considered to be vulnerable. Another example here shows how we can encode a similar situation where instead only a single branch contains the vulnerability. We don't automatically assume that all branches that don't have an explicit fix is vulnerable in this case. And to do this, we replace the fix event with a limit event. And again, all of the rules for this are all described in the pseudocode that we provide, and it's exactly the same algorithm that works for linear version ranges as well. So another guiding principle for us is to keep the format focused on open source. So while we can already fit in some proprietary software and ecosystems without making any structural changes to the schema, we didn't want to compromise the schema's design and increase its complexity by trying to explicitly target a broader scope. An example of this is identifying proprietary software. This is often really hard to do in a generalized way because proprietary software aren't part of any centralized package management system nor namespace. We then, for example, want to add CPEs to the schema because CPEs aren't predictable and don't fit well with our kind of general correctness and consistency principles. If there was a better identification mechanism for proprietary software, this might be something we want to reconsider. So here's a related example of a change that we rejected to add a timestamp range type. So we have ecosystem and Semver ranges to encode ranges of vulnerable versions, but there wasn't a way to record timestamps marking vulnerable periods of time. The justification for this was that this was useful, for example, service providers to mark a time period in which the service was vulnerable. However, we ended up deciding that this wasn't a good fit for open source, nor did it provide any actionable steps for a vulnerability scanner to make use of. So we rejected this change at the time. The main consideration here is that if a vulnerability scanner reported this result, it really wasn't clear to the user what they can do about it. So the OSV schema also promotes a distributed model of home vulnerability databases maintained by the relevant communities or organizations. For example, the GitHub advisory database maintains a database for several ecosystems using the GHSA prefix. The Go community maintains a database using the Go prefix, and Rust also maintains one using the Rustac prefix, and so on and so forth. So this is very much aligned with the way open source works. We have different communities contributing to vulnerability data in a distributed way, and most of them are also open, such that corrections and changes can also be made just by filing an issue or opening a pull request. This model though also has some significance when we're thinking about what to add to the schema. For example, we've seen requests to add EPSS and CISA-KEV status to the schema. However, under this distributed model, it doesn't really make much sense to have this as top-level fields in the schema to be populated by the relevant home databases, because both EPSS and CISA-KEV come from a single authoritative source. That said, though, we still want to make OSV schema easy to cross-reference with this extra metadata, for example, through using the aliases field, so that users can easily cross-correlate between OSV records and additional metadata such as EPSS. And given the federated database model, there's often very specific metadata that home databases want to express, which doesn't make sense as top-level fields because they're very specific to that database or ecosystem. We have extension points in the schema via the database-specific or ecosystem-specific fields where home databases can provide this additional metadata in the form of arbitrary JSON. For example, the Go vulnerability database provides metadata for Go import paths and symbols that are relevant to a vulnerability. GitHub has additional triage metadata specific to GitHub, and Ubuntu exposes the concept of Ubuntu priority in many of their records. The meaning of these are all very specific to those ecosystems or databases. And finally, the last guiding principle for us is that we will never make a breaking change. Breaking a format means that we have to start over again in fostering adoption, and it also causes fragmentation for consumers. What this means is that we will never remove fields nor change them in backwards incompatible ways. And this also means that there's extra scrutiny on adding new fields because the consequences of adding them are permanent. So we really need to make sure we get things right as much as we can, as any mistakes that we regret later will live on forever. I also wanted to talk a bit about driving adoption and getting feedback on the schema. What has been really important for us is to provide an end-to-end set of reference tooling that makes use of vulnerability feeds formatted in OSV. And I'll come back to this slide later. So first, we have OSV.dev, which is an aggregator of all OSV home databases. So OSV.dev provides a web UI for browsing and looking up details of vulnerability records, and it also provides an API to query records programmatically. We also direct users to the specific upstream processes for amending a record. For instance, if we're displaying a GHSA record and a user notices that there's some incorrect information, they can just click a button and we'll take them straight to the GitHub UI for submitting an advisory improvement. We also have client-side tooling through a tool called OSV Scanner and a library called OSV Scaler. And these provide out-of-box vulnerability scanner and libraries for scanning source and container images, and it directly uses the data that we have in OSV.dev. So developers and security teams can use these tools to get a list of vulnerabilities that affect them. So it works by analyzing source code, file systems, or container images to extract the SBOM or inventory of open source dependencies. These are then matched against the feeds in OSV.dev to produce a list of vulnerabilities. And one of the core goals for these tools is to try to make the results as actionable and accurate as possible by implementing ecosystem-specific functionality, such as dependency resolution algorithms or version ordering. And recall that every ecosystem has their own very specialized rules for handling version numbers. So we go to great pains to ensure that we have accuracy there and covering a good coverage of all of the major ecosystems. So providing this extra reference tooling has been incredibly helpful for us in building the OSV platform and in fostering adoption. Providing tools and services on top of OSV data helps foster adoption because users can easily see how OSV works and how it could be integrated into their workflows. And these tools explicitly address the primary use case we had in mind with the OSV schema. So they also serve as a great platform for us to obtain feedback, both for the schema itself, as well as in providing feedback to upstream home databases on their data quality. A lot of the time, some of our users ask us whether if we can support a new feed, and then we redirect them to the relevant upstream community that maintains that feed. And it's a great way for us to convince some of these communities to adopt the OSV schema as well. So what's next? I think OSV is fairly mature at this point in terms of being a schema for vulnerability records. But there are more problems to solve here. Beyond the problem of vulnerability records, one other prevalent problem in the vulnerability management space is that users of vulnerability scanners often have way too many false positives to deal with. One way to address this is VEX, but it's still unclear, to us at least, how VEX applies to open source, specifically open source libraries as opposed to end user applications. Given the distributed graph nature of open source, can we somehow share and propagate vex statements in a way that reduces investigation time for everybody? So here's an example of what I mean. Let's say package C on the left is vulnerable to a CVE, and my application reaches package C, while my direct dependencies A and B. My goal after running a vulnerability scanner that says CVE, I'm affected by the CVE, is to figure out if I'm actually affected. If both package A and package B publish a form of an intermediate vex statement saying that they're not affected by the CVE in package C, then I can also assume that my application is not affected by that vulnerability. On the other hand, if at least one of A or B doesn't have a vex statement or has a vex statement saying they are impacted, then we'll assume that our application is likely also impacted. Now, this is just a small example, but you can imagine this being scaled up to a full dependency graph with hundreds or thousands of dependencies. In this way, we can perhaps share some of the work done to investigate vex applicability and propagate this information through open source dependency graphs so that everybody shares the burden of investigating vex, and we have an easier job to determine whether if we are actually affected by vulnerabilities or not. So one way perhaps for this to work is for there to be a convention for package managers or project source version control to adopt where they store a file that encodes these intermediate vex files. Then users of a package can automatically discover and paste this together with other intermediate vex statements into their own dependency graphs. This will help users determine and reduce the investigation time for transitive vulnerabilities that don't actually impact their application, and allow them to more easily produce a full vex statement for their application. This is all just a very vague idea, and we don't know what this will look like exactly or how it will work in practice, but I think this will be one of the next things for us to tackle in the space of open source vuln management. And that's all I have for today. So thank you very much for coming to my talk.
Thank you. So I have a question about the breaking changes. I wanted a little bit of clarification on that, if you wouldn't mind going back to that slide. So whatever changes you make, they're never going to be breaking. You're never going to update all old records. Mistakes will live on forever. Can't you imagine a scenario in that case where you would then have to add a new field that almost replicates the older fields since you want to change the schema around it? And then doesn't that just bog everything down if you're adding and adding and adding fields, never taking anything away?
Right. So there's a few pieces there. So one, to clarify the backward compatibility guarantee. So what we promise is that if you're a client targeting an older version of a schema, you can safely ignore any fields that you don't understand because you haven't updated your client to support the latest version. And similarly, for clients targeting newer versions, they can always expect all the fields to always be there. They'll never be removed. And the key here, I think, is that we really try to keep the schema to be very minimal. So there's actually a very high bar for us to add a new field. I think that's what's kind of helped us keep the schema quite lean and not introduce a lot of bloat over time. Does that answer your question?
Yeah, I guess so.